Well, hello everyone, and I want to welcome you to our second think tank of 2025. We're here with Derek Chamberlin and Jason Connor, who's with us remotely, to go ahead and talk about optimizing traditional and model predicted fish aging methods. So I'll go ahead and hand it over to Derek as we go ahead and get started.
Perfect. Well, thank you for having us. As well said, my name is Derek Chamberlin, and we also have Jason Connor, who is online right now, and will be taking care of the sort of second half of this presentation. We both work at the Alaska Fisheries Science Center in the Age and Growth program, and our presentation is going to be on traditional and model predicted fish aging methods, which a little bit of background on what sort of spurred these two research projects. About 5 years ago, NOAA Fisheries at the headquarters level funded a strategic initiative to look into developing Fourier transform near-infrared spectroscopy to predict fish age. We sort of we are reaching the culmination of those efforts. And several science centers are looking to implement this method to predict age and develop age composition data for assessments, as opposed to using the traditional microscopic method. At the Alaska Fisheries Science Center, we're looking to implement for the Eastern Bering Sea walleye pollock stock assessment this summer. Assuming all things go well, we have a CIE review this next month, so it's the Center for Independent Experts. And that will be, I believe, February 11th through 13th. We've got a little more information about that at the end if anyone is interested in attending. And then our goal is to showcase the full breadth of work that we've done on this, the sensitivity analyses and stock assessment scientists have run, everything from fish aging error to our traditional methods. It'll be really an end-to-end run through of the development of this method. And we hope that goes well and that we're able to try to implement this in the future. Now, I'm probably preaching to the choir. I will try to keep the introduction as short as possible.
Don't tell us about the spectrometry.
One slide. Have to do a little bit.
You just have to go into
it. So preaching to the choir here, I'm sure we all know that age data is extremely important. Depending on our assessment, we may be estimating natural mortality externally based on age data, everything from growth to reproduction. Within the assessment context, using age data for estimating age composition data, which is obviously very informative for estimating recruitment and fishing mortality. So it's just really driving home that these are very important data that can have really profound effects on our assessments. But it's very time and labor intensive data to collect. So right now, what we traditionally have done for producing ages is using what we call the TMA process, or the traditional microscopic aging. So we have our surveys that go out and collect samples. We also have fisheries dependent otoliths coming back from observers in the field. We get the sagittal otoliths, we section those, toast them to make the annuli pop, which is sort of the brownish tint that you can see on the right image with the annuli enumerated there. And then we look at those under a microscope and count the opaque zones to estimate age. Now, this is, again, quite time and labor intensive. For walleye pollock, an individual production ager can age anywhere between 30 and 50 samples in a day. And we process about 30,000 samples in a year. So to get from 30 to 50 a day to 30,000 in a year, you need a pretty large staff working a lot of work hours to produce those data. And obviously that is very expensive. But the demand for age data seems to continuously increase. There is a constant push to try to increase the tiers of different assessments to get them to be age structured assessments. In order to do that, we typically have to provide multiple years worth of age data just to make that initial leap. And then that also adds to sort of our baseline aging that we have to continuously age new collections for those stocks. But given budgetary constraints, limits on the amount of staffing that we can have, there's sort of a mismatch between that increase in the demand for age data and what we can reasonably do. And so that spurred research into new methods for predicting fish age or estimating age, and that spurred the strategic initiative funding the use of Fourier transform near-infrared spectroscopy. So just the highest level, it's based on the absorption of near-infrared light by different organic chemical bonds in an otolith. So we're able to scan an otolith, get a spectral signature, and the spectral signature is highly correlated with age, so we can develop different models to, once we calibrate a model, to then estimate age based solely on these spectra. And typically that's been PLS models, but we have moved into using machine learning models recently, which are able to incorporate other metadata, are a little bit better at dealing with some of the nonlinearity we see within the relationship. And the process is rather rapid. So on the left is sort of our instrument setup. We don't have to do any prep to the sample, no sectioning, no toasting. We literally just take the sample out of the vial, dry it off on a napkin to remove some excess storage media, place it on the scanning window and hit go. And that whole process takes anywhere from 1 to 2 minutes per sample. So we're talking 30 to 50 samples in an hour as opposed to 30 to 50 in a day. So you can really increase your output using these methods. And these are just some representative spectra on the right. Each line would be from an individual otolith. The general concept is that as age increases, the absorbance increases. And we do have some more informative areas that are kind of highlighted in this very light blue that's a little hard to see, that correspond to different chemical bonds. But with both the traditional aging process, that TMA process, and with NIR, we have to be quite cognizant of aging error. So we're concerned both with accuracy, which would be whether we have some type of systematic deviation from the true age of a sample or of a collection, and precision, which is the spread of our age estimates, essentially how repeatable those age estimates are. And we have different methods to sort of deal with both of those. But the issue is the effects of incorrect age estimation. So this figure on the right is from some stock assessment simulations I did during my dissertation with the Gulf of Mexico gray triggerfish stock assessment. This stock has had historically very high aging error where age was underestimated and you had this sort of curvilinear relationship. So we did some stock assessment simulations, and this is just the relative error in the F ratio and B ratio. And it essentially causes this degree of aging error, underestimating age, causes overly optimistic estimates of both the F ratio and B ratio. So essentially, you're going to think that you have the potential to think that you aren't overfishing when you are, and the potential to think that your stock is not overfished when it is. So can have pretty profound effects, again, depending on the degree of that aging error and if it's not accounted for. But we can try to account for aging error. And what I've seen in most assessments, particularly in the United States, is using a model developed by Andre in 2008. That is in a R package, the Northwest Fisheries Science Aging Error R package. And this is a model that treats true age as a random effect. You feed it multiple age reads, and then it is able to estimate the bias and imprecision of those age estimates, with the caveat that one ager has to be listed as unbiased. And this is sort of a caveat in pretty much any study that uses age data, because it is very, very rare that we actually know the true age of those samples. I think we have one data set with sablefish where we have like 120 known age samples, and that is exceptionally rare. And we'd love to have more. But the package spits out some very useful outputs. We get these figures on the right, which sort of show any potential bias or imprecision, where if this red line deviated from the 1-to-1, that would be indicative of a bias. There is a dashed black line that's kind of hidden behind it. If you were able to see that, that would indicate a reader has bias. And then the blue line would be our standard deviation of age or a measure of imprecision. We also get CSVs that have these age error definitions that can be copied and pasted directly into stock synthesis or another assessment framework if it's able to account for aging error. So we have some great tools for estimating that aging error. Now, within the traditional microscopic aging process, there's really only one step where we expect error to arise for what we're concerned about in the aging process. For estimating age comps, there's obviously different models that people have to deal with, but that's sort of for the aging growth program's purposes, that we pass the data off, and other people worry about any uncertainty on the age comp step. But we go from otolith to microscope to ages, and we really have one source of error, which would be observation error at that observation stage if we're not estimating the actual true age of that specimen, so we can have bias or imprecision at that step. We can try to account for those with age validation studies to validate protocols, so like lead radium dating or bomb radiocarbon. And the caveat there is that we're really validating a protocol, not individual ages for individual samples. And then we can also track the precision using paired readers. What we do at AFSC, we have a collection and we do a systematic random sample of 20% of that collection. If it's a new reader, we test at higher percentages until we are sure that we don't have any bias or precision issues within for that reader for a given species. But the process gets a little bit more complex when we have FTNIR. We have new potential sources for uncertainty and error being added into our age estimates. So the sort of top row here represents the model training process. So we have an individual otolith that is aged with the TMA process and scanned with FTNIR. We can calibrate a machine learning model, which is just represented by this frame graphic. And then we would have test samples or samples that we're trying to predict age for, where we would just scan those samples and we may or may not have a corresponding TMA age, but the TMA age wouldn't inform our model calibration, just be used for looking at how well the age predictions agree with the TMA. So within this process, we still have our observation error at the TMA process, but we also have the potential for process and observation error at the scanning step. So the process error would be variability in that spectra at age. If we had a collection of known age 3-year-old fish that were, say, all born on the same date, we likely would not get the exact same signature from every single one of those 3-year-old fish. It's the same concept as having variability in size at age. We're going to have some variability in spectra at age. Observation error could potentially arise from instrument operator error, if we want to call it that. So this could be if someone put the otolith at the incorrect orientation, or maybe had a very wet otolith that they didn't dry off very well. There could be some degree of error introduced at that step. So we wanted to sort of look to see if operator was having any effect on our age estimates. But in the end, we're really concerned about estimating, looking at how this aging error can potentially impact our age predictions on the back end. So getting some type of distribution of what our age estimates are for a given known age, and then trying to estimate aging error definitions to incorporate into the assessments. So to look at these problems, we conducted a really large paired reading study where we had 552 EBS walleye pollock otoliths selected across 4 different years. And we had 7 independent age readers age these samples. So 7 replicate ages, estimated aging error definitions using that Northwest Fisheries Science aging error package. We also had 6 instrument operators scan these samples. So we had 6 replicate scans to look at that operator error. And then to examine how aging error would impact the performance of our machine learning models, we utilize the multimodal convolutional neural network, which is quite a mouthful.
You wouldn't understand it anyway.
Right. I cannot claim to be a machine learning expert. I don't know if many people can. But this came from Irina Benson's paper that she published, I think, in 2024 on the future of fish age estimation, just using that model to test how our predicted aging error affected our age
So how did
predictions.
you calibrate the neural net in this experiment?
Yes.
That's the next slide.
Yes. So we had 2 model scenarios and then sort of 1 separate comparison in the green, and these colors will track with figures later in the presentation. So for our null scenario, we didn't end up doing like a full simulation where we're simulating a true known age. So we used the original age data from Irina Benson's paper, and that was sort of our null here. And we randomly assigned samples to our train and test data sets. Again, that train is used to calibrate the model. The test is used to evaluate the performance of that model and doesn't inform the actual model calibration. For each iteration, we did fully retrain and retune the model, so we didn't save weights in the machine learning model. So it's just more time intensive, but you are able to better account for any uncertainty that's or any error that is introduced to the model. In this null scenario, we're again just evaluating the model's performance against those original age estimates from Irina Benson's paper. In our age error scenario, did a bootstrap resampling of those age data from Irina's paper, utilizing those aging error definitions that we estimated from the large paired reading, that 7-reader experiment.
Right, with bias or just error?
So it ended up being primarily imprecision that we had a standard deviation at age. There were 2 readers who had a little bit of bias, and I'll show those figures in a moment. But I think that kind of ties into some of the results of this, that we were really just increasing the standard deviation at age as opposed to having a systematic bias in those ages.
Right, so it goes to the emails we've talked about, can you detect bias?
Right, right. In this age error scenario, we also assign that same split to the train and test data sets, and then again evaluated back against those age estimates that were the bootstrap pre-sampled data. We also utilized both of these two scenarios in this age error versus null, where we evaluated the age error model predictions. So that's the models that are calibrated with increased age error, the predictions from those models against that original null data from Marina's paper. So that would be the lower error scenario essentially. And this is to look at how well the machine learning model generalizes. So we're essentially introducing noise into the calibration data, and how does that affect our individual predictions back to those original age estimates. And if the model is hypersensitive to noise, that can be really indicative of model overfitting. So this is just sort of a simple test of the generalizability of that machine learning model.
So are you pooling all 4 years together for this analysis, and are you also pooling spatial strata?
So all 4 years for the aging error, for estimating those aging error definitions are pooled. These are two different data sets. The machine learning model is based off of, I think, something like 8,000 samples. So we're applying aging error estimated from a subset of those samples to the larger data set. And it would be pooled spatially for estimating the aging error. Within the machine learning model, we are able to incorporate different metadata. So their deep weave length is one of the covariates, and I believe Latin long are. So the model does have the ability to hopefully parse out some of that spatial component, but for aging error purposes, that is completely all combined across years and spatial.
Was there different environmental conditions across those years? I think there would have been 19 for 23. So I remember some preliminary 15 years results that suggested that there might be some variability associated with where and the conditions that the samples were collected under.
Right. I don't know that off the top of my head. So I've been with Aging Growth Program for about 1.5 years. So the historical, what things looked like in the Bering Sea in 2015 or 2018, I just wasn't here for that. But they, I believe, temperature and depth of capture is also included as a covariate. So there is some potential to try to account for those, if we have like a warm blob year or something. And the goal with future age predictions is we have sort of prediction intervals based off of these machine learning models. We can look at the biases and incorporate new data as we move forward to try to retrain those models and incorporate any environmental variation that we see. But including those covariates should allow us to not just like smooth across, temperature or environmental differences across years.
Hey, Derek, did you, in this work, look at the different covariates in that model?
So in Irina's paper, she has that broken out. Essentially, there's, I can't remember the exact metric off the top of my head, but there is a measure of how much a individual covariate informed the model. And spectra always comes out at the top. So one of the benefits to the machine learning model is that we don't have to select wavelength regions manually to inform the model, which your PLS models, we do have to do that to a degree. It's able to take the entire spectra and determine what wavelengths are informative to the model. I believe fish length was the most informative non-spectra covariate, and I'd have to look back, but it is, I'd say, off the top of my head, 90% of the model is informed by spectra, and then there's just a decreasing returns with these other covariates. So we can make decisions based on that, on whether it's worth including these other data sources in calibrating the model. If we potentially have like a double use of data concern, which has come up with length data, we can make decisions looking at how well that model performs if we need to use that data or not. So diving into our results, this is just a really simple correlation analysis of the age estimates from those six different scans of the same otoliths. So when we have different instrument operators, we essentially are returning the exact same age predictions using holding the model steady. So the only thing that changes here is the instrument operator, which would have potentially that effect on the spectra. We're using the same model to predict these ages. In our correlation analysis, the correlation coefficient ranges from 0.98 up to 1 with some rounding. So this is really encouraging for us. It's showing that we are really not seeing an instrument operator effect, given some degree of
bias. Right, that's bias. It's not there. There's still variance. There's actually more variance than I was expecting.
Yeah. So we did have some variance in one scanner down here, but for the most part, we have quite a tight relationship between.
Well, tight is relative to what the original aging error is, right? And I don't know what it is for pollen, but certainly scanner 6 and scanner 5 don't seem to. There's more variance there. Even scanner 4 has some
3 to 5 years of spread.
Honestly, they're not one 15-year-old block. But it's more than I hadn't paid attention or hadn't seen it, but it's a little more than I was expecting actually.
Okay. Yeah.
I was expecting really, really, really close. I didn't think they'd be quite that much.
Yeah. I mean, so my takeaway from this has been, I particularly focus on scanner 6 here, which is where we see the largest spread in those data, is that this is something that we need to monitor and examine like the residuals for individual scanners, age predictions to see if we are getting more error in an individual operator, and then try to dive into what potentially they are doing differently, which could be, again, that drying of that otolith if they are not consistently placing it in the same orientation.
Yeah, because I mean, the impression I always had was this was, you were doing it just to prove the point you knew the answer to already.
Right.
And yeah, so there's clearly a competency factor. The R squared itself, I don't think tells you very much.
Well, this would be between those instrument operators.
Right, I mean, so the correlation coefficient doesn't really, when you've got this kind of data, the difference between 0.98 and 0.99 is actually consequential in terms of error. I mean, even, correlation between 5 and 6 is 0.99, right? Mm-hmm. But when you look at the plot, it's pretty clear that 0.99 ain't quite what you're hoping for. Right. So essentially, when you've got a large x-axis range, you always get nice correlations.
Right. Yeah, that makes sense.
It's like doing a Bayesian analysis, increasing the font size of the dots. All that.
Well, we can make these dots smaller, so.
Yeah, the game is making bigger.
Well, yeah. So.
That's interesting.
Yeah. So I mean, my original takeaway from this had been that we had pretty high agreement, with the exception of scanner 6 popped out to me, which it looks like scanner 5 and 4 are popping out a little more to you, Andre. So I think it probably warrants diving into. Right. Well, we know we're going to have some differences. There are different factors that can affect the instrument's performance. We have to do a fair amount of monitoring. So we have desiccants that go in the instruments, keep humidity levels low. Factors like that can affect it, but again, we control for that by regularly replacing the desiccants, running reports. So we really feel like this is probably solely driven by the instrument operator as opposed to different room conditions and or environmental conditions where the instrument is at.
So, I mean, have you ever looked, just taking some of those really extreme points, looking at what the spectra actually looks like for that otolith?
No, I haven't dug into individual samples.
Because I mean, there are one or two there that you'd wonder how they are the same individuals. I mean, and maybe it's just that the spectra, the subtleties of the neural network are so.
And that is something within our QA/QC process. We have multiple sort of guardrails for if you scan the wrong otolith. There's only so much you can control for. If you have 2 3-year-olds in a row, it may not pop out as anomalous if they get mixed up. But at the actual instrument operator station, we have a simple PLS model within our program that you can plot the length predictions for these samples, because we don't have the age data loaded in at that step. And it'll essentially throw a red flag if you have a highly anomalous spectra. And then after a collection is scanned, or in our lab operator manager runs all the spectra through different QA/QC, and I believe they'll present that at the CIE to detect whether there are any outliers, looking at samples that have been logged as crystallized or chipped or broken. We have different rules for whether they can be scanned or not, but they are always, the condition of the sample is always logged, so we can sort of trace the quality of any individual sample. So we do have, this is simply the raw data set. This didn't run through any of those steps, because we were just interested in looking at that instrument operator process. So there is, I think, more potential for anomalous spectra to potentially make it through to this step as opposed to our normal operating procedures.
This is always a question in studies like this. Did the scanners know that this was part of the calibration study, or was this just scanning a bunch of otoliths?
They knew that this collection would be part of the study. Yeah.
So you might expect that production grade scanning would have less precision than this. This all happens a lot. As you do a project and everybody knows it's a project,
right? And
then you turn it into production mode and things aren't quite as precise as when everybody knew this was going to get looked at.
Right. No, that makes sense. I mean, that's definitely something to think about, and whether we should try to replicate something like this without, secretly, essentially, and not letting people know. No, that's a very good point. Valid concern. So these are the aging error definitions that we estimated for the TMA process. So we had 7 readers here. The best fit models were with linear relationship for bias for everyone and linear relationship between standard deviation and age. We see very little bias in general. Reader 3 and reader 4 did have some bias, where you can see that solid red line deviates from the 1-to-1 dashed line. But again, in general, people are falling right along that 1-to-1 dashed line. The standard deviation at age was, say, relatively consistent among readers. There is some variation. If we look at sort of the highest end on that right axis, ranges from about 1.5 years to 2.5 years. So there is some variability, but we're not, and at glancing at it, it doesn't seem like we're seeing anything particularly anomalous where one reader is substantially more imprecise than another reader. And so these data, these aging error definitions were what we used to bootstrap resample the age data for calibrating the machine learning model in the next sort of component of this project.
So I don't know what people are doing these days. It's been a few years since I've done one of these, but we used to do sort of a stepwise AIC thing to see whether or not you really needed, say, 7 different relationships, and you could test, okay, reader 1 and 2 aren't different from each other, reader 3 and 4. Did you go through that?
I did that, yep. And so this was the lowest AIC for testing along those lines. It was pretty close for sharing some parameters across readers, but there was enough variability between these readers that we did need to fit everyone separately with their own parameters. So this is the results, just sort of the usual metrics that we use to evaluate our machine learning models performance for those 3 different scenarios that we discussed earlier. The null model, where we're using that original age data from Maria Benson's model and just randomly assigning those test and train data sets, we have a pretty consistent R² of about 0.92 with some variability in there, just depending on that train test data split. And then an RMSE of about 0.9 years. And this is in line with what Maria reported in her paper. So that's encouraging that is not some effect of the samples that happen to be selected for our train and test data sets. When we bring aging errors to the picture, we do see a decrease in the model's performance. So again, this is bootstrap resampling those original age data, evaluating against data that has also been bootstrap resampled. The R² drops to about 0.87. We see more spread in that R² as well. And similarly, the RMSE increases to about 1.15 years and more spread as well. Interestingly, the age error versus null scenario, where we're comparing the predictions from the models that are calibrated with data that has more error against those original age estimates from Marina's paper.
Right.
We see a sort of return to normal in our model performance.
I don't think what you call age error really, using a test data that has aging error is essentially quantifying your perception of error as opposed to your actual error.
Exactly, yeah. So
so I have no problem using the age error in the calibration set, but when you're testing it, you want to test it on the closest to what you think the real age is.
Right, and that's sort of
That's
the reason we went and did this age error versus the null. Yeah. We wanted to maintain sort of this age error scenario because in practicality, we won't know whether those ages have more error or not. Like we don't have a way to get back to an age that has less error. So somewhat our model performance obviously is going to be tied to the error in the data that we're evaluating it against.
Okay, so I'm little, so there's 6 symbols.
Right.
I get the yellow ones. I get the, I'm not sure what the last one tells me. Because your training data set shouldn't include estimates without age. So if I was doing an analysis, my training data should always have aging error because it always has aging error. But my testing data shouldn't have aging error because that's the true age that you're trying to predict. Do you see where I'm going? So when you know, for each bootstrap replicate, you have some ages, right? You add aging error to some of them, which then goes into the training data set, right? And so I would include aging error throughout on that because when you randomly, in the real world, you'd be randomly selecting hopeless, right? Right. But your testing should, I think, be based on the best estimate of true age. So I think what I'm saying is I would drop the 2nd and the 6th of those panels. So
the
second one is when the aging error is attached to the test data set, right?
Yes. So the blue here, this. So are you saying second, like in?
Yeah.
Okay. I wasn't sure if you were talking about in second this whole.
Oh no. Okay.
Yes, that has aging error in the test that we're evaluating against.
Right. So I don't think that makes a lot of sense.
Right.
I might be completely wrong. And I'm not sure I would look at the 6th one, which is that there is no aging error in the training data set.
No aging error. So this may be
maybe I'm misunderstanding.
Yeah, I think we're really close. The difference here is there was in this particular data point here.
Yep.
There was error in the training data used to calibrate the model.
Right.
Then we get age, in that process, we get age predictions back for that original training data set. It's being evaluated against the original null ages. So we're evaluating against the lower error.
Oh, okay.
So it's just the data from the training set. So maybe it's a little, not presented
this is how well the training data predicted itself given the true, well, the closest to the true.
Right.
Okay.
Exactly.
Yeah, so the only one I don't like is the first
blue. Okay.
Second blue. First blue.
Yeah.
Second blue is fine.
Okay. Interesting. Okay.
Wait a minute. Let me think about that. So the second blue, the training is predicting against itself.
Yes.
And there's aging error in both.
Yes.
So that's what you would see in a real example.
Right, and that's sort of why we kept in both the test and the training here, was this represents what we would see if when we actually have aging error in our samples, that our model performance, and it's logical, your model performance is going to be tied not only to how well that model performs, but how accurate your data that you're evaluating, for instance. And that's sort of one of the challenges here is we have to calibrate models on data that have error that we do our best to estimate, but is somewhat unknowable, and it gets into head banging against the wall areas. But sort of my take home here is that generally we're not seeing, particularly in this green scenario, a massive decline in our model's performance. We end up predicting the same ages, even when we're calibrating on data that has more noise. And that sort of makes sense if we go back to the age error definitions that we use to bootstrap that data, this calibration data. We really don't have bias in these data. Reader 3 and Reader 4 have a little bit of bias, but those are somewhat offsetting. One's underestimating, one's overestimating. So in reality, we're only increasing, sort of the standard deviation of the distribution of those ages, so that your mean age for a given set of spectra is going to be the same within an age class. So it makes sense that we would return similar age estimates even with this slightly increased error. That may break down if you had some type of systematic bias in an individual reader, as opposed to just imprecision. But that's something we haven't examined to date.
So you're sort of testing the system here. And so is this the system that you guys are imagining going forward? You'll have essentially a pool of 4 years that you'll use to train the model, and then you'll use it on that 4 years, and then you have maybe a rolling, so that you add another year's data, you have to have 20% cross checks. Because this, I can just imagine this might look different if you say did that pool and then you predict the upcoming year,
right,
where you don't have any training data.
Right. So we have there are different approaches you could take to updating the model. You could basically look at your age predictions into the future. So I think Marina's model is calibrated off of 2018 to 2022 data. And you can look at predictions into the future and essentially evaluate how well those predictions perform relative to samples that you have also TMA aged without updating the model every year. You can also use those test ages to continuously update the model, which we have sort of an app that's been developed by our IT group for fitting these models to try to sort of centralize this across the science centers, where we can track the provenance of an individual model as it gets updated or retuned, adding in new data. I lost the second part of your question.
Well, I guess just if this is the method that you're imagining using, then this makes perfect sense. But if you're imagining a system where you aren't calibrating the model or training the model every year, then you'd want to be testing that here. You'd want to have a 4-year data set,
right.
You'd want to train it, but then you'd want your test set ought to be your next year.
So we have predictions for a number of years, both for survey and fishery, into the future, where the model has not been updated, including those TMA age estimates. And the model performance is pretty comparable to what we observe here. So I don't have like the specific years data in front of me, but if an R-squared for a test data set here was 0.92, typically, if I'm recollecting correctly, we're seeing about 0.90. So there is maybe a slight difference, but we're not seeing a decline, from 0.90 down to 0.8 or 0.7 or something.
I mean, most of the outlet is the same between years anyway, right?
Yeah.
So you're talking about outlet growth within a smaller period of time.
And there have been concerns: these spectra, are they tied directly to the otolith mass? Are we essentially measuring otolith mass? There have been some studies Michelle Pazzarotti did on the East Coast. She works for the Northeast Fisheries Science Center, where she homogenized otoliths and then scanned a sample of that otolith, so the same mass across otoliths, and we were still able to predict age, and the models performed comparably to the whole otolith samples. So we're measuring, well, there may be some effect of otolith size. We are measuring differences in the ratios of chemical bonds as the otolith grows. So that's the really encouraging thing, that we're not just doing a great job of measuring otolith mass or some other type of metric.
Francis has a paper that says you get about an R-squared of 0.9 just using mass.
It depends on the species. Yeah.
You just have to be careful, because the size and age and growth changes over time. That quickly goes astray.
Yeah. And I've seen some species where you get up into that 0.9, and it can be really dependent on sort of the variability in size and age. There is definitely a link between size and age and otolith mass and age, where I think you get more spread in that otolith mass, as opposed to species that have tighter growth relationships. But so this is just sort of looking again at how aging error is propagating through these models and affecting its performance. It doesn't get us to sort of the applied aging error definition that we're looking for to incorporate into an assessment to try to account for any potential biases. I forgot I had this figure in here. So this is the same scenarios broken down by age. So it's a very noisy plot because there are about 170,000 data points per scenario here. But our models are across these different scenarios are performing quite similarly. This is a test data set. Really where we start to see differences between these scenarios is up at the oldest ages, where we have very few samples to inform our model. So we have still pollock. Yes.
Oh, wow.
Yeah.
How many 22-year-old pollock are there?
Not many. So that's sort of why we see this tail sort of developing here at age 18. We have very few samples out there, so it's going to be incredibly hard to train a model to predict age when you have, say 3 ages and 3 spectra. So in order to account for that, this is such a low number of samples. I think once we see that deviation sort of flatlining, we can automatically shunt anything that gets predicted in that range to the TMA process. It wouldn't really increase the number that we have to age, but that way we hopefully are not.
So are you even, what's the class group in the assessment?
15.
Yeah.
15. But so it doesn't matter for the assessment purposes, but if we're, I mean, those oldest ages have less of an effect on growth parameter estimates as well, but I think that there is an argument to be made that if it's 20 samples or something like that, it's worth 4 hours of work to make sure that we have an accurate age. But
out there, I'm pretty sure you're just getting aging error.
Yeah, that is another consideration. We talked about going back and looking at these samples to see, is that 24-year-old actually a 24-year-old? And because when we look at,
you want to work on orange roughy,
yeah,
500-year-old orange roughy.
Luckily, we don't have to count that far for these. So it'd be tough to production age, about 10,000 of those every year.
Yeah, that's the catch.
Yeah.
So you mentioned putting these back into the TMA process for the really old ones, but we've run into this with, we used to look at surface age versus break and bake, and there's all these other methods. When you do something like a hybrid method, now that assumption of linear or even smooth parametric imprecision doesn't make sense, because you're expecting a breakpoint. If you say everything over 17, you're going to age using traditional methods, you might expect the CD, the imprecision to go up and then back down.
Right. You would almost need like
a step function, which last time I checked wasn't in Andre's program.
No.
There's a spline.
I don't even know if I've got the code for it.
Well, I think you wouldn't be able to estimate it really anyway, because I think your original paper showed you need at least 500.
You need a lot of data.
But the problem is sort of conceptually, if you're pasting methods together, you've kind of broken the approach that Andre has.
Right. Yeah, that makes sense.
You might almost be better to live with some bias and increased imprecision from one method than to try to put the two together. I know that's the conclusion we came to when we were used to try to put surface and break and bake ages together.
Right.
When they would break and bake something over 20, you just couldn't figure out how to splice it together and have it make any sense.
No, I mean, that absolutely makes sense. If we would be quite anomalous to have, bias and high imprecision for one age class, and then you immediately shift back to low precision or, high precision and low bias.
So before you go forward on this figure, obviously the older ages are really notable, the difference between traditional and 15 years, but you're also seeing some, would it be bias there and say?
Oh, there's bias.
Yeah, you're getting too old for young fish, underage for middle fish.
So
it's kind
part of it is because of these box plots are stacked next to each other. So like these would be accurate all three.
that one.
But yes, there is a little bit of age over prediction, say here, and then some age underestimation here.
Is that even a year?
So I'd have to look back at the actual
5. I mean, it looks like about half a year.
Yeah. there are, within all these samples, the root mean square error was about 1 year.
Okay.
So we could break that down by actual age class, but there is some variability there within these age estimates for sure.
Yeah. Before you go on, Jim, do you still have a question? You go ahead and unmute if you'd like. Can't unmute. Fantastic.
Jim, I'll be back at the office. Is it Thorson or Ian?
Ian Elliott.
I'll be back at the office after this, so I can always swing by.
You should be able to.
And you can shoot me out in private. So. But sort of the next thing we were concerned after, looking at how aging error affects our model's performance was estimating aging error definitions for FT&IR. And so I'm going to step through a very bad example into a better example that sort of spawned from some rabbit holes that I fell down and Andre yanked me out of.
Did you? Did you get out?
Yeah.
What a river told me. What?
It took me a long time to get out of that rabbit hole. But, this is from a test data set. So that same test data set from Marina Benson's model, where we have the paired TMA age to the FT&IR age. And when we try to estimate the aging error definition, pairing just these two samples, or these two age estimates, this has been a pretty common theme that we get back odd results. I know you've experienced this. It's been folks trying to estimate these aging error definitions in the Southeast have experienced it. And what sort of happens is all of the uncertainty seems to get shifted into the TMA age, and we're predicting almost perfect NIR ages. And so this has been a bit of a head scratcher, but after talking with Andre, having these two age estimates, we really can't estimate the error among these readers. We don't have enough data to inform the model, or enough readers to inform the model. And so just the results we're getting back are spurious. And I think this approach was sort of fun because this is how age error definitions are typically estimated, just with two readers. And so we have a large data set when we just have one reader for TMA and the FT&IR, but obviously a smaller data set if we need to include a second. So Andre's recommendation was that we do just that, use the same data set, filter it down to samples where we have both a read age, which is our original reader who reads the whole collection, and a test age, which is tested at 20%. And when we fit the model with two TMA readers, we get a much more realistic age error definition, where we see some slight overestimation of these younger ages, which is what we saw in that figure 2 slides ago, and increasing underestimation at our oldest ages. If anything, I would argue that this underestimation, this bias here, may be a little high, and that I think is likely due to the low sample sizes we have at those oldest ages. Because if we have so few samples that even have an original read age for these oldest age classes, we only have 20% of those that are actually tested. So we're representing, a dozen samples for these oldest age classes. So we need to, evaluate whether we need to change our sampling protocols so that we can better inform these models to estimate the age error definitions. One thing that did stick out to me a bit on this was that the
TSA has come out pretty low.
Yes, the standard deviation of age for the TMA comes out very low. This oldest age class is only about half a year. When we compare that to model run that is fit, so it's the same figure that was on the last slide. These are the same two readers here, just compared to each other. You can see that standard deviation of age is much higher when we're directly comparing TMA to TMA. So my question, and something that we need to investigate, is this due to the samples that we have available? Are we not able to properly inform the model to estimate that standard deviation in age for the TMA ages because we lack sufficient data? Or is this some effect where there's a true age random effect within the model? Are the NIR ages impacting this process and the subsequent fits? And to do that, we need to run a simulation. And that is what Jason Connor has been working on. And so that process is sort of, I'll let Jason run through it, but there are a few more steps that we have to take in some future work to really dial this in, and we'll present more on it at the CIE. But
Do you know who your CIE reviewers are, by the way?
we do Niels Anders,
Oh, okay.
Cadigan,
Oh, no.
and then I'll have to look after this, someone from from Denmark who has experience with machine learning models, mostly in acoustics, but we're the pool of fisheries machine learning is not massive pool. I think it's OLAVs, but I'll look that up after we wrap. But
So this is CIE just for the 15 years aging?
yes,
Separate
targeted.
from the Pollock CIE.
Yes, so we will, work with Jim and
You're
likely have
running
a
a
presentation.
statement as you're sitting here.
I'm wondering about the order. So are you
Yeah.
gonna do this one first and then Pollock, or Pollock first and then? this
Yeah,
one?
we're in February. We are February 11th through 13th. I think Pollock is in May sometime. So we'll definitely, we'll work with Jim and we'll have a presentation. But this will be full 3 days specific to FTNIR. The vast majority will be on walleye pollock and EBS cod. There will be some presentations from other science centers just showing sort of the breadth of the research that has been done. We'll have a presentation on sablefish and some of the sensitivity analyses we've run. And we'll do the full gamut from traditional age estimation to looking at error in these models, to sensitivity analyses within EBS and PCOD assessments. So this presentation was sort of looking at a trial run. What are the holes we can poke here, and the things that you would want us to improve on before we have the CIE next month?
Last question.
Yeah.
Have you thought about doing the same thing with the 15 years that you did with the TMA here, which is to actually go back and use the individual scanners as
Yes.
replicates and fit them so that you have double reads for both methods instead of just?
Oh, no, so I have done it just running, those 6 NIR scanners, no TMA ages. You obviously get quite tight fits.
Right.
I have not done it where it's, TMA1, TMA2, NIR1, NIR2, but that is, it'd be interesting to
We
see.
have
what-
2 methods,
Right,
but we have double reads for both methods and cross reads. So you have kind of statistical power to look at both bias and imprecision simultaneously for both methods. But here, if you only have single reads for 2 methods, I can see why it's sort of confounded.
right. Yeah, I'd have to think about that a little more. One of the challenges with sort of those replicate ages that we had in scans was, so we did a sample uniform distribution across years for ages 1 to 10, and then everything above age 10. But we only sampled from samples where we had both the original read and test stage. And in hindsight, that sort of limited the age ranges that we saw. So I think our oldest sample was like 15 or 16 within that data set. So when I ran the age of definitions just based on, say the 7 readers and an NIR, we don't, while we're limited with data here, we didn't have any data out sort of where the curve starts to taper off and we sort of reach that asymptote. So we were getting more of a linear relationship, which when we have that broader age ranges, we know that's not what we're observing. So that's that I ran with the 7 TMA readers and just the mean NIR age estimate, but I could run it. It would be interesting to see what effect you have if you run it with multiple NIR. But yeah, so again, like good time for any more questions, and then Jason can take over and talk about the age error simulation that he's working on.
Maybe we need to replace my software. It's only 15 years old now. Is there anything we've used 15 years without changing it?
If we can just know the true age.
Yeah, it's so much easier, right?
I wrote it.
Yeah,
Added some more.
yeah, but
They just updated it to TMB.
yeah, I don't think that was me. I think that was Jim Colson.
Oh, you're right, it was.
And some of the relationships that you can fit now have changed a little bit. Like it was linear and curvilinear. Now it's linear and Michaelis-Menten, which
Yeah.
take
That could have
same
been.
form. I don't know if like the spline is still in there.
Yeah, I put the
True age
spline
is
in.
there.
I don't know if it survived.
Yeah.
But you ever had enough samples to estimate it?
Yeah.
Yeah.
Usually 2 parameters is all you're gonna get out
Yeah,
of it.
no, you're right.
Right.
But yeah, it's been such a long time. No one's really, everyone's got,
Nobody wants.
we got, yeah, that's right. If you can't prove it's rubbish.
Well, we're hoping that's not what we prove.
Thanks for the paper, nothing else.
No.
I want to have unlike Punch et al. 2008.
Well, it just sounds like punt it all 2025, right?
Yeah. A rebuttal of my own paper. Just becoming like Ray, really.
Except if he does them the following.
That's
year.
right. I think 15 years. It doesn't take 15 years.
It's Stillborn 2025 A and B, yeah.
Well, Carl, who could remind himself in the same paper.
Did Jim not have a question anymore?
Yeah, Jim, do you still want to ask your question, or are you all good?
Oh, no, thanks, Derek. I'll touch base with you later, just on the,
Okay.
on the matter. Appreciate it.
Yeah, absolutely.
Okay. Right, yeah, I'm not seeing any other questions online, so if not, speak now or hold your peace for the next 45 minutes till we're done with the presentation, and Jason, I'll let you take it away.
Thanks. Well, it won't be 45 minutes. Good job, Derek, speeding through all those slides. Go ahead and move to the next slide, please. Yeah, so I'm building a package, and the past month I've been doing a lot of debugging, getting the simulation going. So for the slides I'll present today, we have 200 iterations of every scenario, and the input data are from our Pollock study from last year. So the 7 TMA readers, we identified who our least biased was by BIC, and sorry, still sick, and just input the zero bias reader as our quote unquote best reader from the study, and then the test 2 in the double tester scenario is our second best reader, and then our reader is who performed the worst, basically, with bias and standard deviation. So the plan is, we're streamlining the code right now with these scenarios, but then probably next week I'll get around to doing something a little wilder, and then of course before CIE review we want to play around with FT-near input errors. Next slide. So this is deviation, not deviance. I wanted to present bias first. So the rows are percent testing of the original sample. So 5%, 10%, 20% is our current procedure. We test 20% of red ages to look for agreement, and then 30%. To me, is self-explanatory. This is just the estimated minus true bias, and bias doesn't seem to be very much of an issue. At 5%, we're having a little trouble, I think, estimating the bias through Andre's program, but even if we drop down to 10%, I think we're pretty safe on the bias side, and that that bears out what Derek presented already, is that through our procedures, we're even though we don't have known age samples, a test set of 7 readers, some of whom are considered expert in reading Pollock ages, and some who just kind of got pulled onto the project because they were available and we needed more readers. That because of our training processes, our physical training processes, not our model training processes, we do a really good job of managing our bias, or keeping our biases low.
Sorry, I was paying attention to my code, not to you, but remind me, this is all simulated data here?
Full simulated, yeah. So the data
on the TMA and unbiased estimates on the age readers?
Yes. Unbiased for reader number 1.
Okay, so
or not reader number, tester number 1. But yeah. Derek, go back a slide.
Sure.
Yeah, so the solid lines are standard deviation, and the dashed lines are the bias, the input bias for the simulation. So each, I should have said, the age comps are simulated for each iteration from a log normal distribution. And so we have, and the sample size is 2,000. So we have 200 times 200 iterations for a read set of 2,000 otoliths, and they're each independent, sampled with these errors.
Okay. And the bias is what is the definition of bias? Is it the slope of the dashed lines?
No, it's the intercept.
It's the intercept.
Yeah. So, or no, sorry, it's the y-axis value.
So the bias at age 0? Because the bias is parameterized as a slope.
Right, so the bias here for this reader would just be this line here. So at age 10, the bias would be about a year.
Right. So when I'm going to the next one, it's the next slide was in absolute terms.
Mm-hmm.
Right. So if you go to the next one now, it says estimated bias minus true bias. The good news, it's surrounding 0. I like that. But I don't know how to interpret 0.025 because what is 0.025? What is the bias? It's the slope of the bias function, which is what it usually is. That's increasing. That's 1 over 20 years or something like that, which is 0.025. So 0.025 might not be all that great. So I'm trying to get a sense of what is the value you're trying to estimate. Does this make sense? What I'm trying to explain?
I think so. If we go back to,
I'm happy that you're at 0 on average.
If we'd go back to Derek, can you slide back to your TMA study output slide?
This one?
Yeah. So the inputs are just from the basically the SS3 output file, the CSV file, or the model output file. I take them right from the TNB model in the code. So they are the categorical bias estimates for each age.
Oh, it's the additive difference between the true value and the thing. So bias here is the difference between the true age and the expected age.
Yes, exactly.
Okay, so the difference between those, and which in a case of a straight line.
Yeah. So go back down, Derek, please.
Sort of changes with age.
Yeah. So we can see for the reader, for the reader on the double tester scenario, or both, I use the same errors. For the reader, the dash line is the bias, and so at age 17 or 18, which is our cutoff, we have like 1.4.
Okay, and so if you go to the next slide, that 17 is 1 point. So it's of the 1.4, the error is 0.025.
Right. So that's the difference. That's the difference between the estimated bias after we throw it through the model, the aging error model, and the input bias for that age.
Okay, the reason I was asking is I'm sort of surprised how constant the relative error distributions are over age, because if you think about it, at age 2, the bias would be 0.01 years. At 17, it's 1.4. Yet the distributions look remarkably constant in terms of relative error, or in absolute error, not relative error.
Absolute, yeah.
So Because I would
Yeah.
expect those distributions to get
Especially if it's forced to be linear.
So I'm a little surprised by what I'm looking at. Maybe I'm
Sure.
just-
And yeah, the error distribution for the model for bias was linear bias. But perhaps because the input biases are actually pretty low, pretty close to zero. When I try some wilder scenarios, we may see something that might be a little more expected. So again, I think, yeah, I agree that I would expect over the course of 17 age categories that we would get to bigger differences. But if it turns out that the model seems to be estimating pretty good when the tolerances are small to begin with.
That orange reader, the single tester reader, is the one who has the bias on it in this figure. There is, I mean, it's subtle. There is an increase in the mean bias with age.
Oh, yeah.
For sure. But so we would expect the model, I mean, to perform really well estimating the unbiased reader.
Well,
right. Like
yeah.
if it's unbiased and you parameterize it as unbiased.
Yeah, you get a zero.
Oh, right.
It's the bias reader that you're after.
Yeah. But I think Jason may be onto something, that it is the degree of bias that maybe if we, right now this isn't incorporating that sort of curvilinear relationship that we see with.
Right, but it's still, the absolute bias is going up as you get older.
Right.
So, I mean, I wouldn't, it goes up a little. I'm looking at 20%.
Right,
You can
it's
see it gets
large.
wider and then it sort of hits an asymptote and just keeps constant. And I'm not sure why that is. Anyway.
Jason, would you mind refreshing us on what the 5, 10, 20, and 30% are?
Yeah, that's the proportion of the red sample that is tested by a secondary or tertiary reader.
Perfect, thank you.
Mm-hmm. Okay, so that we can come back to bias. I think the more interesting topic from this is CV and standard deviation. I did just the absolute difference between estimated CV and the true CV for this plot, and the red box on the single tester is what we currently do, which just from this simulation study was very reassuring that at least we aren't under testing for our current error estimates. However, when we add a second tester, our model estimated errors or model estimated CVs, standard deviations are much smaller, or are much tighter, more accurate predictions of those. And that's kind of what's exciting for us on the production side, is that it seems like for sure we should consider changing to 10% testing and having 2 testers read those 10% of the samples, because that's going to increase our confidence in our standard deviation estimates that we provide for a collection. But even at 5%, we're seeing that we have a slightly better but also comparable error estimates for the reader. We're focused on the reader. We are generally giving the stock assessment modelers the reader errors, although they can choose whichever error estimate they want to include. But if we compare 5% double tester with 20% single tester, we're well within the same ranges for the purple bar, and that would go ahead.
Jimmy and Ellie, can someone unmute Jim? I've just got an email from him saying he's feeling unloved and unappreciated. He's in therapy for a while. And we can go.
I apologize, Jim. I did not see anything on
Can you
my end.
unmute him so you can?
Yeah.
You should be
I think
unmuted right
you can hear me now. Can you hear me now?
Yeah,
Oh, yeah. You got it,
have at it, Jim.
I have a completely different question. That's the slowest you've ever responded to an email, Andre.
I'm trying to keep that. I've got non-working code.
No, if I could just ask a clarifying question on the slide real quick.
Yeah,
So the panel that you've highlighted in red is showing the error in the CV estimates. And I just want to
Yeah.
make sure I understand it, because it seems like age 1 are really low CVs to begin with, right? It's really easy to determine an age 1 fit.
That's probably a mistake, Jim, because the software has some constraints down at that end where, for example, having a CV on an age 0 doesn't work. So sometimes the very first one is a little funky. That's a technical term.
Oh, good to know. Thanks.
yeah,
Yeah,
good to
no,
know that. Yeah, good to know that too. We we were hoping that was the case. Because if we go ahead and go to the next slide, Derek. Thank you for pointing that out, Jim, and for not having a more difficult question.
I think when you do interpret this, you do need to be a little careful about which ones are going to be, because there is that sort of, it's soft,
It's the
right?
hockey stick. So.
Yeah, it's got
Yeah.
it's because you don't want to do CVs of 0 and it affects 1 as well and things like that. So
Yeah. So in this, this is just percent relative error of the SDVs, and we've eliminated H1 in this plot just to except it added it on to the end. That's obviously a coding issue. Did something. Oh no, that's the dashed line. All right. So this is actually, obviously it's presenting the same metric of random error for our age reading, but in terms of percent relative error, maybe a little more informative, especially if we get down to 5%. We're underestimating on the single tester side. If we test it at 5%, we'd be seriously underestimating our error, which could definitely be an issue for our use of them in stock assessments. So at the very least, we should continue doing 20% single tester, but I think we are building a pretty good argument here, just from the preliminary data sets of decreasing, potentially decreasing our workload. Now it's not a straight decrease. If we went to if we go from 20% to 10% double testing, that would probably represent an increase in work, because we have then 2 people who are having conversations with the production reader on the test sets. So there would be a little more work involved, rather than having one tester read all 20%. But again, at 5%, I think we do a really good job in this scenario, with this model, in estimating the SDVs for the reader.
One thing that this raises, perhaps unrelated to the topic at hand, is looking at the single tester, which, as we pointed out, is pretty common. It correctly said that we tend to use AIC to say, can we detect them? So it'll be interesting to see from the simulated data set how often you're able to correctly detect which are there differences. So, when I've got 2 readers, the first thing I do is I run them with the same age reading error vector, because, hey, that's the simplest model. And the interesting question here is, would you be able to actually reject that hypothesis if you only have a single tester rather than 2 testers?
That's a good question, because I think that the default when estimating these definitions tends to be you have those 2 readers and you just run them we're sharing parameters.
Yeah, I mean, although realistically they're humans as opposed to different techniques completely, but that certainly is the way we, I always start, and to be honest, I really am able to reject the hypothesis that they're different.
It also gets to how you're planning to use it, because if you're planning to use it for production aging, and you don't know, there might be a new reader next year. If you don't want to have to reestimate the relationship, you should pool all your readers, so the variability should reflect all the readers, because you might have new readers next year. But if you do it the way you've done it, every time you add a new reader, you got to reestimate everything.
Yeah, well, I mean, that's what they do pretty much. Like the worst example is sardine, where I think they've changed age readers virtually hourly. And so I think we had 16 age reading error matrices in the assessment last time. Yeah, I didn't. And then they wouldn't say who was who, because there was one age reader who sucked.
Because if you tell them, then they change and you have to reestimate it.
Yeah.
You can't provide feedback unless you're willing to redo the whole analysis.
Personally, I think that there's a strong argument to be made for updating the definition annually. If we look at, since we have to consider, I think, two things. We have our own internal QA/QC procedure. So if we have a sample of 2,000 pollock, those are not all read by the same reader. So let's say that goes into let's say just the EBS survey sample. Those are split down into smaller collections. They're read by multiple readers. There can be other testers, and aging error definition is estimated by pooling the readers and the testers. So you're getting really a cross-individual estimate of that uncertainty. But like you say, if that composition changes the next year, one person tests more often, one person reads more often, somebody retires, that aging error can change. Even if there's anecdotally, we've seen a general increase in the difficulty of a lot of species over time, but there can be annual differences. I remember hearing that the warm block years were difficult, very difficult. I mean, that was in Pacific cod in particular, and cod are a nightmare to begin with. Yeah, I think that it's pretty straightforward to estimate these. And something I'd like to look for our program to do is try to incorporate this into our workflow. Right now, the assessment authors estimate the definitions. Try to incorporate this into our workflow, and we produce standardized reports that maybe each year we can just reproduce an updated definition by fleet. Because there are differences between fleets as well. Because fisheries collected throughout the year, your edge interpretation can have a big effect on whether something gets bumped to the next year class or back. So there's different error. And so I would argue that the common practice of just using a single definition for an entire time series may not be the most true.
Once again, we have pollock. The rest of us feel embarrassed when we see pollock.
So there's a lot of different ways you can build these data sets. I don't know what the underlying data look like, but I remember from putting these together. So you might have a subset of your data that has both methods and multiple reads. And that can be one data set. You can fit multiple data sets simultaneously. That's going to have a huge amount of power. Whereas if you divide it up and say, here's all my double reads for one method and all my double reads for another method, but you're estimating separate random effects for those two data sets, you have very little power.
Yeah, the new version of the program essentially puts in a line for every outlet. And so you can have missing, so you can have your minus, well, I don't know what it is, -1, I guess. -1, the B2, minus.
So you're using all the double and cross reads you can for every.
Yeah, that was one of
that's perfect.
And then it works out which outlets apply to which.
And for our purposes, we very rarely have missing data within our double reads and with these NIR sample sets. It's going to be limited to a handful of samples where, an otolith went flying and got lost under a desk. So there was no test stage for it, but there's a scan age or something like that. Or the otolith couldn't be scanned because it was broken, but we have double reads. So it's really the exception that we wouldn't have all three age estimates.
That's great.
Within these data.
But yeah, the software now can do that.
Yeah.
Jim, if you want to go ahead.
Yeah, you put one data set in. I think you can still have multiple data sets, but I don't think anyone does it.
Jim, do you want to go ahead and ask your question?
Yeah, sure. Just to clarify again, on the 10% double tester, does that take the same amount of person hours as the 20% as single tester?
Yeah, so I don't think so. I mean, it'd be pretty close. but there's logistics of getting the test set to the second tester. There are probably ways that we could streamline that, but at that point you might be coordinating disagreement conversations between 3 people rather than just 2 people. So I think just like slightly logistically more complex, but I think quite obviously worth it in this scenario.
And I think one thing that might be important to mention is these simulations, the testing at these different percentages is using our current protocol for selecting samples, where we just have a systematic random sample, select a number 1 through 5, and you go every 5, essentially. We will explore utilizing a stratified random sampling approach, where we can potentially get more samples in these older age classes. Right now, we're seeing good fits within those age classes, but I think potentially once we add in an NIR where you have more bias concerns and a larger imprecision, we may need more data. I wouldn't be surprised if we need more data to inform the model and need to change our sampling approach. It just makes sense. You want to have as uniform a distribution as possible to try to estimate these bias and standard deviations of age.
Yeah, and I think as a first slice, this is given our current staffing, myself not included. I wasn't any of the test breeders. I was just coming on board when this project got off the ground last year. But this is our current worst case scenario for pollock, which I think is a good place to be in. Hope that makes Jim happy. Yeah, well, the next step will be adding CIE, or not CIE, adding FT-NIR as a reader with that curvilinear bias, and also playing around with what if we get the worst reader possible? That was the anchovy reader that you're talking about? Sardine, yeah.
There aren't many ages to choose from, but how old do they live anyway?
Yeah.
3. Well, at the moment you can't get 0.
Yeah, and eventually, we'll need to take a look at other species. But for right now, we're lining up for the CIE presentation. But appreciate any more questions or critiques or something that you would have liked to have seen as far as an informative slide would be good to know.
I mean, the other thing, just generally, I think these are great. I would have found it a little easier to see some of these if they, this is fine as a summary, but a plot that actually has an x-axis that's the age, and on the y-axis is a line which is the true value, and then box plots. I know it's the same thing, but it's just one. I like to see what the true value was and what the estimates look like. I mean, it's just a different way of expressing the same information, but for people with small brains, almost starting with one of these plots and then saying this is what it looks like for 20% in terms of, true in absolute terms, and here's it relative, just to jump us through so we know what these things mean. I mean, this is far better than I would have thought.
Yeah, I'm really I mean, Jason's done a great job working on this. I'm really interested to see what happens when we introduce more error into the simulation. Right now, it almost seems like we're rendering it something easy to start with.
I mean, what just out of interest, what initial values are you giving the estimation method? So, because you have to give initial parameters for things. As long as, I mean, it's always a good idea to check if you're not giving it the right answers and it's just failing.
Right.
Giving you back.
Jason, do you know off the top of your head? There's initial values within the DAT file, I believe.
Yeah, so we usually jitter the initial values from the true values just to avoid that kind of stuff. I can't remember whether I had, because I did some simulations probably a lot slower than Jason did, given 2008.
No, I don't remember what those are.
Yeah, because you have to write the DAT file, you might as well just add a little bit of noise to the initial values to make sure
That makes sense.
it's not getting itself.
Yeah.
Really, my question is, how do these results so far compare to the original paper?
You know,
Because the original paper had a range of sample sizes
yeah,
and a range of bias, and so you ought to be able to compare back and see,
Yeah.
are you getting similar performance now?
And you also tested curvilinear bias, and I think
Yeah,
that's
very-
where some of the sample size issues came in, which is what,
yeah, this is linear, you're only estimating one
Yeah.
parameter, which
Yeah.
is, it's actually not a difficult thing to do, but once you start getting into curvilinear, and that's why I've sort of got into, which I don't think I did in the paper, but I can't remember, you know, it's model selection, because, you know, when I wrote it, I didn't even think about it. Why, decide which model to use.
And on the practical side, I know we have some folks from other aging labs that I think are on here remotely. We do plan on making this available as a package as well, because right now, I believe the state standard operating procedure for labs is there's just been the essentially an arbitrarily chosen testing percentage. People can look at different age ranges, different longevities of species, add in different expected errors, and try to optimize their testing procedures. So our goal is to, clearly with this introduction of NIR, our goal is to try to increase our efficiencies, and testing is a big time consumer. So that's sort of what spurred this, and it just so happens to be hopefully very useful in dialing in how we estimate those definitions for NIR as well.
Yeah, it's cool that this is actually being, and is this starting to help your issues that we were getting, the weird? Okay, let me rephrase, not your issues generally, but your issues related.
I don't think so.
I don't think we're gonna have time. Coming from me, that was a little rough, wasn't it?
Well, you know my issues better than most.
Yeah, but we don't have time for one.
Yeah, I think
We got
the
30
results
minutes.
you showed at the end of doing multiple TMA readers, but then I think extending that to multiple 19 years.
Yeah.
I can do that.
Yeah, I think if I did that again, it'd be interesting to see if I got more reasonable results.
Yeah. I mean, those results definitely look more reasonable for estimating the NIR definition.
Yeah.
Sort of the next step is to then test it within this framework. The simulation that Jason's working on will get us a much more robust answer versus visually, this looks better than the NIR ages being perfect in the kind of crummy run.
Yeah. Well, I'm sure you're a little chirp. Jim, if you want to go ahead and ask your question.
Yeah, thanks. I have a general question for the group, if in the spirit of think tank. Just especially Chantel and Andre or whoever else is there, Ian. So I've set up the model so I can deal with multiple age error matrices within years and across years. So it's completely arbitrary, but I'm not sure if that's a good thing or, exactly what. So we're starting to get these types of differences in their duplicate data sets. And I'm really seeking guidance on how to set up designs and actually testing, and then beyond testing, being able to say something about them. So I'm just wondering if anybody has any initial thoughts on approaches on the actual assessment and using these data.
Yeah, I mean, I'm assuming when we talked about it, we thought you'd be putting in some TMAs that you age that you didn't NTIS or whatever that thing is, and then a second age comp from the sort of production ages. So if they're independent TMA ages, they would go in, which we continue getting because we want to make sure that Andre's program is great, but it's real residuals. So yeah, so basically you would expect that you'd have multiple age comps for the same fleet and year or survey, whatever it is, and each of those would have their own age reading error matrix. I think that's where we got to.
There are actually two different approaches going on for that. So that's the approach Northwest has talked about, is using NIR as more supplemental to increase their sablefish aging. We are looking at a wholesale switch, so you would only have NIR comps.
So you'd be still doing TMA aging.
In this testing framework.
Right.
So whatever number pops
Yeah.
out, let's just, assume we're sticking with one reader, we would test 20%, we would have TMA aging from those, but that would be.
Well, the test data sets would be available to.
Right, yeah, that's a good point. Yeah, those would absolutely, we can make those available.
I mean, I think our sense
Every
was,
sample.
we like it, but you don't want to throw your babies out with the bathwater.
So isn't that kind of double dipping though? If you pick your test data set and you've used that,
Not your training, not your
not the
training.
training data
Training,
set.
yeah. So this would be the 20% that you leave out anyway, just to test it afterwards.
So then you have to bootstrap both sets of age comps to get your starting sample size,
Yeah, there's some,
which is going to be
Well, I
low,
don't
which
think
is
it'll-
going to be low for the 20% test set.
well, but for pollock, it's probably not.
All right, 20% of
Big
20,000 is pretty good.
Fair. For whatever, that's not quite the catch, but for yellow eye, it might be. We have actually, N is greater than the total number in the catch.
I guess before we.
But generally, I mean, I think generally from an aging error point of view, Jim, having the ability to, if even with TMA, if you go back and look at the ages that have used these things, Chantel knows these assessments a lot better than I do, but with Hake, I think we've got a couple of age reading error matrices, don't we?
We have one for each year.
There you go.
Yeah, and a lot of years are the same, but there's select years, and I think Pollock would have the same issue where Hake has years where you have large year classes moving through, and then you have aging error and bias from the traditional agers because they know they're reading a certain year of ages, and the number 3 year class is going to be huge. So if there's any uncertainty, you're dumping that maybe.
That's still such a scary, it just.
Yeah, and so we were talking about, because we've got those ages, and we estimate a separate aging error for those specific years to try to account for that. So we know some years are perhaps a little bit more biased and uncertain than others. But we also now have 15 years ages, and you don't see the same spikes of cohorts in the 15 years ages. And now we're trying to figure out, is that because you don't have that reader bias in there just from knowing a certain cohort is going to be big? Or is there something else going on in 15 years? And is something in the model? All those questions. When you don't actually know the treatments, how do you figure out which ones quote unquote matter?
That's interesting. We see that too, that it doesn't, tends to smear out strong year classes. And as far as reader bias, I mean, there's been work on that historically that showed that it didn't really exist. That was quite a while ago. For Pollock, didn't exist.
Oh, yeah.
For Hake, we did a double blind experiment and it exists.
Yeah.
If you read a 90 otoliths and in the 91st one, it's hard to read, you're gonna put it the same age, you just put the last 90.
Right.
Yeah.
I think, Jen, were you referring to like bias overall in our age estimates, not like an individual sample along that? So like there have been multiple age validation studies, but again, we're just validating a protocol there.
Yeah.
And we try to use QA/QC measures to track any reader drift. But it's, that's a large assumption that the protocol properly is still being properly applied is producing unbiased age estimates. But there definitely, I would agree that there definitely is some year class effects, year class specific aging error. Right now, I think there's a strong class of 6-year-olds Pollock. Quite a few get defaulted into that.
Well, basically the nice thing about these types of analyses, if you've got the basic, if you've got a protocol, you can do those. The analysis doesn't take very long compared to deciding which model to use for a stock assessment. So it's just good practice.
So where do you guys land then? I'm still interested in Jim's question. Use both data sets, or sounds like that was sort of the consensus.
I think if they're independent data sets, I would love to make sure that all the fancy math that goes into this, I still want to see, are you missing the TMA ages compared to the production
So
ages?
where does your training data set come from then?
Training data sets used to update the algorithm.
So the training data set that we have right now, like the core of the training is from a 4-year span. We then have the potential to retune the model each year, which would come from these test reads.
Correct. The training data set's built on the 20% test data, right?
No, it's built on original read ages
Okay.
that we aged everything from those collections. Those
Right.
original TMA ages were used to build the comps, went back and scanned them, built the training model on that. Moving forward, we will only have a proportion of the sample that is tested. Everything will be scanned, but only a proportion will be TMA aged. And you can retune the model, adding in those new TMA subset ages.
But the point, I guess, that is being made is that if you once you use the TMA ages in the algorithm, you really shouldn't reuse them somewhere else.
Right, but those TMA age comp, those NIR age comps need to have the TMA corresponding TMA
Right.
ones removed.
Yeah, exactly. Yeah. If you've got something left over, then
Yeah.
it's worth bringing into the analysis.
Which in particular for this stock, I mean, the large number of samples we have, we could still have hundreds of test samples.
Then Jim,
What about testing TMA all by itself versus the model run with FT-NIRS all by itself? So not having that danger. And what do you interpret? I mean, we have almost the same number of sample sizes, I think, right, Derek?
You should have precision with the FT-NIRS. Because even if you've got some aging error, you should have much larger ends, basically, before you tune. I mean, that's the other thing. I don't think, have we decided how we're going to adjust the effective sample sizes for these, like, I mean, I could easily see the FT-NIRS being its own fleet for tuning purposes, for example.
Yeah, and I think it depends what data set you're reading, like survey versus
Right.
fishery, because that input sample size is not directly related to the number of ages.
Right.
It's the number of toes, number of trips.
But if you're
And I
getting
think
a lot,
Alaskan is a little different.
Right.
And so that's.
but if you're getting a lot more samples, particularly from a fishery,
Mhm.
the number of toes has a different meaning when you.
Yeah.
So at the moment, I don't know how we end up having samples per toe, but now it's sort of, as long as somebody can stick a otolith under a machine.
Yeah.
And this does, I mean, not only, we'll see the efficiencies we gain over time, but this does open the potential to increasing the number of samples that we're able to provide. Right now, we're looking at maintaining current capacity, but if we're able to maintain staffing levels, right now we age all the survey samples, with the exception of some unique collections that we didn't age Northern Bering Sea this past year. So those were relatively lower priority versus the EBS survey. But fishery, is heavily subsampled. So we do have the potential to maybe increase some of those.
And that's why I was suggesting talking to Pete and his team. So Brett Stacey is working on some of that in terms of how to calculate effective sample sizes. And
Right.
so it's sort of orthogonal to what we're doing.
Strategize the samples we select so we.
I mean, the thing that, I mean, maybe this is an Alaska problem, but it's certainly a West Coast and certainly Australia problem, which is how do we increase the number of species that we get semi-decent sample sizes for? And the problem with that is it's just the startup cost for FT-NIRS is non-trivial. And you have to go to age in the first place.
But just to be clear, Andre, for input sample sizes, if you collect 2,000 otoliths for TMA and then have another 2,000 that are using FT-NIRS, you wouldn't change the input sample size.
Well,
You would change the aging error.
You certainly change the aging error, but it also depends on how those FT-NIRS were sampled. So if you're, I mean,
Well, assuming you sample the same way. I mean, we're not changing the program.
You would hope that 10,000 FT-NIRS at least is worth more than 100 TMAs from one sampling unit. So if you take one trawl and you get 10,000 fish versus 100, I'm hoping that you're not going to give it the same weight as you would the 100.
I think
Andre, that's so
Might be.
far from reality. I mean, we're talking about, first of all, for pollock, we only age about 3,000 in the fishery. And I'm just saying that, right now we have the equivalent number of FT years. I mean, it varies a bit, but I wouldn't change the sample size just because it's FT years data.
Oh, no. It really would be.
The Pete's bootstrapping method, though, actually includes the aging in precision.
It does, yes.
So if you got a much different precision, better or worse, it would change the input effective sample size a little bit using Pete's method, which I think is actually the right way to treat ages.
Yeah.
And this is me just thinking out loud, so tell me if this is dumb, that kind of thinking about, maybe with the pollock example or, any West Coast species in the future, where you've got a lot of years of traditional ages from a specific source, and then we switch over to FT years. And most of our data weighting methods basically apply a scalar just up and down to that whole data set.
I would keep them separate plates.
That's where I was going.
Yeah, no.
At least to make yourself,
Well, you want to see plots by status.
confirm that the data themselves, given the aging method, is not having different influence in the model. This FT years more, I don't know what the word would be precise, but match the model expectations greater than traditional.
OSA residuals, wait until we know enough.
Okay.
I think I agree with you conceptually, but using Pete's method, if you had a big change in the imprecision, it would already be included. So you'd actually you get the scaling, you get some of the scaling.
I still would, just a priori, I like to have lots of foods maybe.
Just to Ian, we've already, Pete's run.
It runs so slowly they can't do sensitivities.
Yeah, well, I review things without worrying about what it's someone else's problem.
Yeah, Ian. Sorry, Ian. Yeah, we've already run. I haven't looked at the results yet, but we've done the traditional TMA for using Pete's method to get sample size, and then he's gone and done it with the same data set with FT years. So for the CIE review, Derek, this was just the end of last week. We worked on it. So yeah, he's helped us out. So sorry, I haven't looked at it yet, but I would have the answer to that question on that difference anyway.
That'll be really interesting to see. That's great.
Okay. Any other questions from the room or anyone online?
This is cool stuff.
I do very quickly want to thank the folks who did all the aging. That was a pretty monumental lift a little over a year ago again. This is the whole aging growth program, plus a few folks who have retired from the program.
You realize that's bigger than like 5 or 6 countries worth of ages?
We're a little artificial.
We're literally on 2 guys.
So just, it's been a really huge collaborative effort.
They're all smiling. They obviously haven't worked for the day.
This was Morgan's going away party a year ago. And then this QR code will take you to a website that we have for the upcoming CIE review. It is open to the public. It will have in-person at AFSC, also virtual options. The schedule is posted. Links to some documentation for passive reviewers to check out is there. So yeah, feel free to scan that or email me with any questions, reach out. I really do appreciate you all having us and letting us do a run through and poke holes in things before we go into the next lion's den. So.
Well, interesting to see what Anders is going to say because he's the TMB guy.
Oh yeah.
There's Neil are going to give you guys I don't know, they're going to give you guys some.
No, they're working.
Well, Noel will be here in 2 think tanks giving his own. So if you want to talk to him.
That's right. You can go to the CIE and it's a therapy session.
I might be before him, so I have to stay quiet so he doesn't.
I just think it's a couple days after this. I think it's literally February like 17th. So
Oh,
you might be
okay.
able to de-stress
Right after, yeah.
and take revenge on Noel if you need to.
Well, thanks, guys.
Yeah, thank you again
Appreciate
for Derek and Jason for going ahead and talking. We'll have our next think tank in 2 weeks with Moses Lerber, who is one of Noel Yosham's students. So please feel free in 2 weeks to come join us 9:30 a.m. then. Thank you again. And we will see you in the future. And Jim Inelli politely said February 18th for Noel. So off by a day.
Oh, 2 points are my favorite.